Welcome back to another episode of Practical Electronics and Circuits 101. In this series, I explain the fundamentals of electrical engineering with a focus on practical knowledge, so that we can apply what we learn to actual projects that I'll be doing in future videos. Today, I'll be giving an introduction to electric motors, and specifically, I'll be talking about brushed and brushless DC motors, AC induction motors, stepper motors, and servos. And I'll also be talking about motor drivers and control circuits. The goal of this video is to give a broad overview of what these motors are, what they're used for, how they work, and explain the basics of how to use them, and to give as much information as possible in a 30-minute video. Now before we begin, I wanted to quickly mention that the link to the full playlist of this series is in the video description. So if you're a first-time viewer, then I highly recommend watching the full playlist as well. Also, if you enjoyed these sorts of educational videos, then be sure to give the video a thumbs up and subscribe to the channel if you haven't already. Alright, so let's get into it now. Again, this is just an intro to motors, and I'll only be going over the details that I feel are the most important to understand for practical purposes. Now there's many different types of motors with different characteristics and intended use cases. So with that said, let's begin by explaining how motors work at a fundamental level and the theory behind them. Now, all electric motors take advantage of properties of electromagnetism in order to transform electrical energy into mechanical energy. If you recall from a previous video, I talked about coils and inductors. When an electrical current runs through a coil, it radiates a strong electromagnetic field. Now, if you've ever played with magnets before, then you know that when you place two magnets close to each other, then they'll either be attracted to each other or will repel each other, depending on how their polarities are orientated. The same concept applies to coils and their electromagnetic fields, and this is what motors take advantage of in order to turn the rotor shaft. A basic DC motor contains coils and permanent magnets. When the coil is energized, it radiates an electromagnetic field, and this field will interact with the permanent magnets. In this context, coils are commonly referred to as electromagnets, since they have the same effect as permanent magnets, except they can be electronically controlled. These components are orientated in such a way that it will continuously spin the motor's shaft as long as the coils remain energized. But it turns out there's many different ways to orientate these components, and each method offers different pros and cons. Also, larger motors typically don't contain permanent magnets, but rather they completely rely on electromagnets, since these can produce a stronger electromagnetic field. So let's now go over some of these different types of motors. As I explained in a previous video, electrical current is commonly delivered in two different formats, alternating current and direct current, or AC and DC for short. Direct current provides a stable voltage which remains constant, while alternating current provides a swinging voltage that oscillates between positive and negative voltage, and this produces what's called a sine wave. Now, some motors are classified as DC motors, while other motors are classified as AC motors, and the way each of them is constructed is different. So let's quickly go over some of the differences, starting with DC motors. There's many different types of DC motors, but generally speaking, the most common types can be classified as either brushed or brushless DC motors. Let's first look at how brushed motors work with this simple example and diagram provided by Wikipedia. The main components are two permanent magnets of opposite polarity, two rotor coils, a commutator with two different contacts, and two brushes which make contact with the commutator. The two rotor coils and the commutator are directly attached to the shaft and spin along with it. When a voltage is applied to the brushes, the current flows into the commutator, which then energizes the coils. Each coil is wired opposite of each other so that they always produce an opposite magnetic field. Blue represents north polarity while red represents south polarity, and this also applies to the permanent magnets as well. In this current state, The blue coil is being pushed by the blue magnet since they're the same polarity, and likewise, the red coil is being pushed by the red magnet. This causes the shaft to rotate, as we can see in the second picture. Now in the third picture, we can see the shaft has turned to the point where each coil is now next to a magnet of the opposite polarity. At this point, the rotational force drops to 0. However, we can also see that the two leads of the commutator are also turning, and the brushes that they make contact with will become reversed once it gets past this point. When this happens, the polarity of the coils will also become reversed. Now the diagram doesn't really show it for some reason, but just imagine the color of these two coils becomes reversed. And as a result, we now have a blue coil next to the blue magnet and a red coil next to the red magnet again, which means force will be applied to the shaft again and it will continue to rotate. This process continues as long as voltage is being applied to the brushes. And if we wanted to reverse the direction of the motor, all we would need to do is reverse the polarity of the input voltage. But I'll talk more about motor drivers and controllers later in the video. Now, one of the problems with this design is that it's not very smooth. Like I mentioned, there's a period of time where the force being applied drops to 0 right before the coils reverse their polarity, which leads to choppy and inconsistent rotation. In order to improve this, more magnets and coils can be added like you see here, which results in much smoother operation. However, one of the biggest problems with brush DC motors is that the brushes and the commutator need to make physical contact with each other, which means they wear out over time, don't have a long lifespan, and require maintenance. Brush motors can also produce a lot of electrical noise on the circuit, which can be an issue if the circuit isn't properly designed to deal with that. They're also not very power efficient when compared to brushless DC motors, which I'll talk about here in a second. But some advantages of brush motors is that they're simple to build and are very affordable. They also offer very high starting torque, which might be necessary in certain applications. They're also easy to control, since all you need to do is apply a voltage with 2 wires. Another fun fact about DC motors is that they can also be used as generators. If you manually spin the rotor of a DC motor and connect a multimeter to the motor's leads, then you'll notice that it produces a voltage which can then be stored in a battery or used to power other devices. There's lots of different types of generators, ranging from massive ones found inside hydroelectric dams, all the way to portable gas-powered generators that you can set up in your backyard. But anyway, generators aren't the focus today, so let's move on and talk about brushless DC motors. As their name implies, brushless motors don't contain a brush and are typically configured like you see here. Now the permanent magnets are directly attached to the rotor, and the coils are attached to the outer frame, which is referred to as the stator. The coils are energized in such a way that they're constantly switching polarity back and forth, but they do so at slightly different times from each other, in order to keep the rotor moving at a continuous rate. Simple brushless motors only have 2 magnets and 3 coils, but more magnets and coils can be added to improve efficiency, torque, and smoother rotation. One of the main benefits of brushless motors is that there isn't any physical contact between the parts, which means that they have a much longer lifespan and don't require much maintenance. Brushless motors also offer higher efficiency, higher speed, lower electrical noise, and they typically weigh less when compared to brush motors. However, the construction and operation of brushless motors is significantly more complex. Like I mentioned, the coils are constantly switching their polarity back and forth, and they need to do this at very precise timings. Unlike brush motors, where this mechanism is directly baked into the physical design of the motor with the commutator, brushless motors require an external electronic controller to manage the timings of all these coils. Most brushless motors also include several Hall effect sensors in order to keep track of the position of the rotor. All these things I mentioned not only add to the total cost, but also adds complexity not just to the design, but also from a control perspective. Also, something to note about these controllers is that they contain inverters, which convert DC power to AC power before being sent to the coils. So in a way, these technically are AC motors, but there's a number of differences when compared to traditional AC motors. So let's talk about those now. So like I mentioned earlier, not only are there many different types of DC motors, but there's also many variations of AC motors. But one of the most ubiquitous is the three-phase AC induction motor. So let's take a quick look at how these work. I won't be going into too much detail on these because these days they're really only found in large industrial applications. The technology itself is also quite old, and one of the original induction motors was a two-phase design created by Nikola Tesla in the late 1800s. And soon after that, the three-phase induction motor was created. The construction of these motors is actually quite simple and extremely elegant, but the physics of what's happening with the magnetic field is incredibly complex. Along this stator, we have three sets of coils, with each set being driven by a high voltage AC signal that are slightly out of phase with each other. When two signals are out of phase, it essentially means that one of the signals is very slightly delayed compared to the other. But in this case, we have three signals that are out of phase with each other. Now keep in mind that AC signals oscillate between positive and negative voltages. When the voltage of one of these coils is positive, its magnetic polarity will either be north or south. And when the voltage becomes negative, the polarity will shift to the opposite one. Since these three sets of coils are out of phase with each other, the electromagnetic field that they create together ends up rotating in a circular motion. Now if we look at the rotor, this is composed of a bunch of metal bars arranged like how you see here. This is referred to as the squirrel cage. When a magnetic field is applied to a wire, or in this case the bars, this creates an electrical current that flows through them. And when an electrical current flows through a wire or a bar, this in turn creates its own magnetic field. So what ends up happening is that the magnetic field of the squirrel cage interacts with the spinning magnetic field produced by the coils, and the end result is that the rotor gets rotated around. Now in the terminal box is where the three AC signals are connected to the coils. And it turns out there's various ways these terminals can be connected to each other, including the delta configuration and the star configuration. These different configurations change the way the signals interact with each other and how they flow through the coils, and each method has its pros and cons. This was a simplified explanation, and I've left out a bunch of details, but what I covered should be enough to give you a general idea of how they work. Like I said, the design of these motors is very simple but extremely elegant. Their functionality is completely controlled by natural phenomenon, and the interaction between pure sine waves and electromagnetic fields, which, in a way, can almost be described as sorcery. This is a stark contrast to brushless DC motors, which basically rely on brute force using sensors and complicated computer-based controllers, which do offer better performance these days, but it took a long time for them to get there. Even though three-phase AC induction motors are roughly 130 years old now, they're still used today in large industrial applications because they're economical to build and are extremely reliable. But now let's move on to more specialized motors. Let's look at a few that aren't only useful for industrial and manufacturing applications, but are also commonly found in robotics and hobbyist projects you can do at home. While there are many other types of specialized motors out there, the two I'll be focusing on today are stepper motors and servos. So let's start with steppers. Stepper motors are a special type of brushless motor that are designed to move in discrete increments as they turn around. Now, what I mean by discrete increments is that there's a finite amount of positions which the rotor can turn to. So let's say we start from this position here. Then we turn to a different position. Now let's say we want to return to the original position exactly without any error. While this might be possible with a regular brushless motor, It's not always guaranteed to return to the exact same position, and there likely will be some error, even if the error is extremely tiny. But depending on the application it's being used for, even the smallest amount of error might be a problem, which is why stepper motors are used in these applications that require exact positioning. Stepper motors contain toothed stator plates which sort of look like gears but don't function the same way. These gear-like contraptions don't physically touch each other like you might expect, but rather they create special magnetic fields which allow them to lock into exact positions with each other. They're also able to move one step at a time according to how their teeth are arranged. The more teeth, the more positions the rotor is able to lock into. It's also possible to position the rotor in the middle between two teeth using advanced control techniques such as half-stepping and micro-stepping. Stepper motors are used in a wide range of applications including robotics and industrial applications. But another application you're probably familiar with is 3D printers. As you can imagine, 3D printers need to be extremely accurate in order to produce good prints, and they need to be able to return to exact positions. For example, when you push the home button, then you expect it to return to the exact same position every time. But now let's move on to servo motors and give an introduction on what these are. Unlike other types of motors which can continue to rotate indefinitely, servo motors, on the other hand, can only rotate 180 degrees. So let's say this is the default position of the horn, which is this arm-like component here, and this gets connected to whatever you're trying to move around. The horn is able to move up to 180 degrees in this direction, but not any further than that. And likewise, the horn is also able to move 180 degrees in the opposite direction, but not any further than that either. This functionality is useful in applications where you don't want continuous motion. One example could be small airplanes and their flaps. Flaps are used to change the shape of the wing, which alters the plane's lift and drag. The range of rotation for a flap will depend on the specific plane, but generally speaking their range is pretty limited, and are certainly less than 180 degrees. Now, while commercial airplanes typically use hydraulics to control the flaps, smaller airplanes and especially RC planes will typically use servos to control the flaps. Servos are also commonly found in many industrial and manufacturing applications and also robotics. For example, these pan and tilt camera mounts contain two small servos. Now, from a construction point of view, servos are basically just a typical DC motor, a control circuit, and a gearbox that's designed to increase the torque of a shaft. This means that even a tiny little servo motor can offer a surprising amount of torque for such a small package. Speaking of torque, let's now move on to the next part of the video and go over some of the main specifications you should keep in mind when purchasing a motor. Like I just mentioned, torque is an important spec which basically tells you how strong the motor is. If you're planning to move big heavy objects, then you'll want a motor with a high torque rating. Torque is generally given in the unit of Newton meters, but can also be given in different units such as pound-feet, pound-inches, and more. These units all mean the same thing in the end, and can be converted into each other using mathematical formulas. Similar to how Celsius and Fahrenheit both indicate temperature, it's just a matter of converting one unit to another. Now, another obvious specification to consider is the speed, or RPM. This tells you how fast the motor is able to rotate. So let's say we have a motor that's rated for 1000 RPM. This means that if we powered a motor at full speed, then counted how many times the shaft makes a complete rotation in 1 minute, we would count 1000 rotations in 1 minute. Likewise, this specification can also be given in rotations per second or rotations per hour, and more. It's simply a matter of converting from one unit to another. Now, something else to consider is that there's an inverse relationship between speed and torque. A motor with high torque will generally be lower RPM, and likewise, very fast motors will generally have lower torque. But the physical size of the motor, its power rating, and the quality of its coils and magnets also plays a role in these specs as well. Something else to consider is that many motors also contain a gearbox in between the rotor and the shaft. Some gearboxes are configured to increase the speed of the shaft while also lowering its torque, and other gearboxes are configured to decrease the RPM but increase the torque. Now, some other important specs to consider are voltage, current, and power. Every motor will have a maximum rated voltage. If this voltage is applied to the motor, then it will rotate at its maximum speed. And if you give it a lower voltage, then the motor will turn at a slower speed. Keep in mind that most motors will still work if you apply a higher voltage than what it's rated for, and they will spin at a faster speed. However, doing this will likely cause the motor to overheat and fail, so it's not recommended to do this. Likewise, if you apply a voltage that's too small, then there's a chance that the motor won't turn at all. So there's generally a minimum voltage required to get it moving. Now, depending on how much voltage you apply to the motor, its required current will also change. The higher the voltage, the more current the motor will need, and you'll need to make sure that both your power supply and the driver circuit can supply enough current. Now, as I mentioned in previous videos, the unit of power can be calculated by multiplying the voltage and the current, but the power rating also has a direct relationship to the motor's torque and speed rating, since power can be converted into the unit of work, and work can be converted into torque and speed. I won't be getting into the details of these mathematical conversions now, but hopefully you're starting to get an idea of how these electrical units and physical units are all related to each other. Now, really quickly, a few other specs you should be aware of are the stall current, no load current, and starting current. Let's say you connect a motor to a load that's too heavy for that particular motor and it gets stuck, or in other words, it stalls. The stall current tells you how much current the motor will consume when this situation occurs. And again, you'll want to make sure that your power supply and driver are capable of delivering this. Likewise, if the motor doesn't have any load, then naturally the amount of current it will require will be less. This is called the no-load current. And not surprisingly, a motor without any load on it will also be able to spin faster. This spec is called the no-load speed. And lastly, the starting current tells you how much current is required to start spinning the motor from a resting state, since it turns out that more current is required to start a motor compared to if the motor is already spinning to begin with. Now, this wasn't a complete list of all the specs you'd find in a motor's datasheet, but I think I covered the important ones. So let's move on to the last part of this video, which is PWM, motor drivers, and controller circuits. And specifically, let's look at how to control brush DC motors, since they're the most common, lowest cost, and easiest to control. In fact, the easiest way to turn a brush DC motor is simply to connect its leads to a DC power supply or a battery. So let's say we have a motor rated for up to 12 volts. We could simply connect it to a 12-volt power supply or a battery, and the motor will spin at its maximum speed. Now, if we connect this motor to, let's say, a 5-volt power supply instead, then the motor will spin at less than half of its maximum RPM. Now, if you wanted to be able to turn the motor on or off with a physical switch, you could put a physical switch in series with one of the leads like you see here. But the most useful way to control a motor is by using an SBC such as the Raspberry Pi or a microcontroller. In a previous video where I covered transistors, I showed how to connect a Raspberry Pi to a transistor to control a motor, so I recommend watching that video if you haven't already. But in that example, I wasn't able to control the motor's speed and wasn't able to reverse the direction of the motor. So now let's talk about how we can accomplish these two things. In order to control the speed of a motor, pulse width modulation, or PWM, is the best method. I've explained what PWM is in a previous video, but basically PWM is a square wave that can be set to a desired frequency, and the duty cycle of the square wave can also be controlled. A 50% duty cycle is on 50% of the time and off 50% of the time. A 25% duty cycle is on 25% of the time and off 75% of the time, and so on. The duty cycle can be set anywhere between 0 and 100%. So now, if our Raspberry Pi's output pin feeds a PWM signal to the transistor, we can control the voltage that the motor receives. If we have a 12-volt power supply connected to the motor and we feed a 50% duty cycle, then the transistor will effectively give around 6 volts to the motor, which means the motor will rotate roughly at half of its maximum RPM. Now, if we change the PWM duty cycle to 75%, then the motor will effectively receive around 9 volts and will run at roughly 75% of its maximum speed. But like I mentioned before, PWM signals can also be set to a specific frequency. Higher frequencies means each cycle takes less time to complete, or in other words, they have a shorter period. One of the benefits of running a higher PWM frequency is better power efficiency. However, different motors will have a different range of frequencies that they can work well with. Generally speaking, a good place to start with small budget motors is a frequency between 1 kHz and 5 kHz. However, the problem with these frequencies is that they fall into the audible frequency range, and the motor itself will radiate this frequency, which can be pretty annoying. That's why the ideal PWM frequency for motors is anything above 20 kHz, which is the upper limit of what the human ear can detect. For example, 25 kHz is a common PWM frequency since it isn't audible, but not all motors will respond to such high frequencies, especially budget motors. Unfortunately, not every motor will include this specification, in which case you'll need to determine the optimal frequency by trial and error. So that covers how to control the speed of a motor, but what about changing direction? In order to reverse the direction of a DC motor, we need to replace the transistor with a larger circuit called an H-bridge. It's called an H-bridge because it's composed of 4 transistors, resistors, and diodes arranged with a motor in the middle. Now, while you could build your own H-bridge like you see here, it's better to purchase a dedicated chip like this. The Texas Instruments L293D is an old H-bridge that was originally released around 40 years ago, but is still common today because of how cheap they are. You can easily find packs of them on Amazon for less than $1 each. And there's also various module boards with some of them having header pins designed to plug straight into an Arduino or Raspberry Pi. These modules make things a little bit easier, but to be honest, they're not really necessary, and using the dedicated chips instead is still really straightforward to use. Also, it turns out this chip actually contains 2 H-bridges, so you can connect 2 motors and have full control of both of them, as you can see here. Alternatively, you could also treat each H-bridge as a half bridge, in which case you can connect up to 4 motors. But if you do this, then you can only drive each motor in a single direction. This image is taken from the datasheet, and the older 293 non-D model also requires you to add these clamping diodes. But these older models are no longer available, and the newer L293D models have these built in, so you don't need to worry about adding these diodes. Now let's quickly go through some of the specs you should keep in mind. First is the supply voltage, which is rated up to 36 volts in this case. This means that we can safely connect a 36 volt power supply to power motors that are rated for that voltage. Next, we can see the output current is 600 milliamps per channel for the L293D. So you can only use these with motors safely that are rated for 600 milliamps or less. Now the peak output current tells you the absolute maximum current the chip can provide for a short time. In some cases, for example if the motor stalls, then it will try to pull more current than it typically needs when running normally. So if the stall current of a motor is greater than 600 milliamps and less than 1.2 amps, this is okay only if it stalls for a short period of time. If it continues to stall for a long period of time, then it's possible the chip will overheat and damage itself. So generally speaking, you don't want to go over 600 milliamps, but in certain circumstances, it can handle more current as indicated by the peak output current, but only if it's for a short amount of time. Also, adding a heatsink to the chip can help with this as well. And finally, the maximum PWM frequency that this chip can handle appears to be 5 kHz according to this source, although this spec doesn't appear to be clearly stated in the official datasheet. Now, as far as connecting everything to the chip, this is pretty straightforward as you can see here, but I'll be going into more details on this in another video where I show how to use hardware PWM with a Raspberry Pi, so stay tuned for that. But anyway, like I said, this is a really old chip and there are much better alternatives these days that are based on MOSFETs, which provide much better efficiency and higher output current. For example, this small board is based on the TB6612FNG and is an affordable option that can provide up to 1.2 amps of continuous current and 3.2 amps peak current, which is considerably higher than the L293D. But more importantly, this chip can handle PWM frequencies up to 100 kHz, which is important if you want a silent motor. However, one drawback of this chip is that it can only handle up to 10.8 volts maximum, which is considerably lower than the L293D. Like I said, this is a good budget option for a MOSFET-based H-bridge, but keep in mind that there are even better options available than this. But of course, those also come with a higher price tag. At the end of the day, choosing an H-bridge will depend on the motors you're planning to use with it and their maximum voltage and current ratings. Now, like I just mentioned, the next video I have planned for my Raspberry Pi playlist will show how to set up hardware PWM in Python. And I'll be doing several hands-on examples, including one with an H-bridge, and we'll also be showing how to use servo motors as well. It turns out the controller used for servo motors is already built into the motor itself, so all you need to do is connect power, ground, and a PWM signal to control the servo. So stay tuned for that video if you want to learn the details of how to use these devices. Now, when it comes to controlling brushless DC motors and stepper motors, these are a bit more complicated, and I don't plan to cover these in that next video. But at some point in the future, when I do a project that requires one of these motors, then I'll get into more details on how to use them. But for now, we'll just be sticking with brush DC motors and servos for the projects that I have planned in the near future. But anyway, I think that wraps up pretty much everything I wanted to go over today. Like I said, this was just an intro, but I think I covered a lot of ground, considering how massive of a topic electric motors are. Hopefully now you have a general understanding of how motors work and the differences between some of the most common types. If you learned something today, then be sure to give the video a thumbs up and subscribe to the channel if you haven't already, and stay tuned for projects that apply what we learned today. As always, thanks for watching, and I'll see you next time.